Okay, so welcome everyone. Right now we've got Anchor Data here to talk to us about large-scale machine learning for e-commerce. Anchor Data is the research manager of RIT Boston Group and a principal scientist in RIT. He obtained his PhD in robotics from Carnegie Mellon University in 2010, where he was an NSF Graduate Research Fellow. He has worked at IBM Research Labs, Amazon, and Akamai before joining Rakuten. He is the principal research his principal research interests are in machine learning, deep learning, natural language processing, and computer vision. So please welcome Anchor Data. Thanks.
Thank you for the kind introduction. Can you guys hear me okay in the back? Yes? Yeah? Okay, excellent. Thank you. Well, welcome to the talk. Thank you very much for taking out the time to come here. As introduced, my name is Anchor Data. I'm RIT Boston Manager. And as you can also tell, this is a technical talk, so I hope you ask a lot of hard questions because I have several members of my team and I'll just give them the hard questions. So let's talk about what we're doing in Boston.
Audio very low again.
Sorry?
Audio.
Is this better? No? Well, it is on. Do we have a volume button?
Hello?
That's better. Okay, excellent. So today we'll talk about two projects that we are doing in Boston. The primary goal of these two projects is basically to increase our customers' experience when they come and use our e-commerce website. So we are primarily driven by making sure our customers have wonderful experience on our e-commerce website. So it goes without saying that I don't have to explain to you what is Rakuten Ichiba in this room. As everyone knows, it's our e-commerce platform in Japan. But what some of you might be surprised with is the scale of this business. Ichiba has roughly 42,000 merchants on the platform. There are 230 million individual products on the platform, and this number grows daily by a significant number. And these 230 million products are organized into 40,000 different categories, into different sub-leaf categories in a taxonomy. So a typical data on Ichiba looks like this when the merchant uploads their product. We have an image and then a description of the product from the merchant. This is a perfect example of unstructured data.
From the microphone. Yeah. You can do source maybe.
Can I use that? Sure. Thank you.
Okay, I hope this is much better then. Okay, so as I was saying, this is a typical example of what merchant would upload on Ichiba. It's an example of unstructured data. You have text description on the right-hand side, and then you have image on the left-hand side. But let's explore a minute what I mean by unstructured data. So data can be in two formats, structured or unstructured. It goes without saying, structured is basically when it's organized into rows and columns. This is your typical Excel spreadsheet. A human actually goes and they will structure the data into relevant factors, into columns, and different data items reside in rows. Unstructured data, in contrast, shown on the right, are things like reviews, are things like product catalog, are things like search queries, which are basically like text blobs, where computers today do not have a good idea of what to do. That's why we have to design machine learning systems to extract information from these unstructured data and use that to improve our business. Now, interestingly, and I don't know if some of you know this, but the amount of unstructured data in the world dwarfs the amount of structured data. And in fact, this actually graph is already pretty outdated. In 2011, IDC, which is a big research firm in US, came out with this graph where they said that the amount of unstructured and semi-structured data vastly exceeded structured data. So when you think of structured data, you're thinking those Excel tables, you're thinking what goes in an Oracle database, for instance. But unstructured data are things like video, think YouTube, and things like tweets, blogs, clickstreams, so many different things. And this is already 5 years old, so you can imagine in 2016, 2017, there probably is no comparison. Maybe it's a 10:1 or 20:1 ratio. Now, on the e-commerce platform, we have plenty of unstructured data. So product catalog is the largest unstructured data piece we have on the e-commerce platform on Chiba. So product catalog is simply a collection of products that are being uploaded by the merchant continuously every day onto the platform. When they upload the product, they upload the title, description, they'll upload an image. All three of them are unstructured data. And we want to understand all this information, the images, the title, the description, and then do two key things to this unstructured data, which is to organize and search this unstructured data. So let's talk first about the first key task, which is organizing. What do I mean by organizing? So what we want to do is take the unstructured product catalog on the left. This is our input. This is what the merchant is giving us. Do some kind of machine learning in the middle and organize it into a taxonomy. Taxonomy is nothing but a hierarchical collection of different semantic concepts that lie at different granularity. So at top level, you might have higher level concepts like clothing, houseware, luggage. At lower level, you may have women's clothing, men's clothing, children's clothing, and within men's clothing, you might have more subdivisions. In fact, on Ichiba, the whole tree looks like 40,000 nodes. That's a lot of nodes. And on the left side, your product catalog is several hundred million. So what kind of machine learning can we do? So let's understand the problem a little bit better. So our input is on the left-hand side. These are women's shoes, and they come with picture, they come with title description. We need something in the middle, which we're going to call the machine learning model. And the goal of this model is to take the input and pass it into the correct subcategory. So this last example is depicted by orange, and it goes into the right category that it's a pump. That's what we want to accomplish. And the middle task is what the team is trying to learn. So how can we do this? Well, let's start with the simplest possible machine learning model, which is a decision tree. Well, what is a decision tree? It's a very fancy name for something that we do every day. You have a goal or objective, you want to go somewhere, and you think about, okay, how will I go there? Is there a train? If there's a train, which train? So this is, you're following the decision tree. So here, we're just trying to see, okay, does the person like computer games? What do we know about the people? Well, we have different people. We know their age, we know their gender, we know their occupation. So the computer automatically learns the relevant attributes that are necessary to make this decision. It'll ask simple things like, is the age less than 15? If yes, the person is likely to like computer games. If no, maybe less likely. Another prerequisite, do you even have a computer? If you don't have a computer, probably you don't like computer games because it's a prerequisite. Now, the interesting thing to note here is we supply the left-hand side, and the computer algorithm comes up with the right-hand side on its own. It does some optimization. There are some very nice theoretical properties here. I won't go into that detail, but the interesting part is the computer is learning the algorithm on its own. Now, starting with a simple algorithm, what do we do next? Well, we do what everybody would do, which is we learn thousands of these models. And this is where the large scale part comes in. You learn thousands, tens of thousands of these for hundreds of millions of elements. And the computer is making small decisions in each one of the trees. And we have a very cool optimization step in the bottom that combines the result from these tens of thousands of decision trees. And that's what we're trying to do. The new product comes in, computer makes tens of thousands of decisions, and finally at the bottom there's another model that combines each one of these predictions and we were able to find which category to put that new product. So we took this fancy machine learning model and put it into a very large architecture, which is very scalable. It hides a lot of complexity that is hiding behind the diagram. But this is a rough architecture of our large-scale machine learning system for classification at Ichiba scale, which, as you know, is very large. It has 3 primary steps. So on the left-hand side, a new record comes in. So let's say today, a merchant goes online and uploads a new product data, maybe a new shoe, maybe a new bicycle. And then we do normalization of text, which basically means we do some pre-processing, we do some deduplication. These are necessary input modification steps. And second, we extract large number of features. We extract hundreds of features in some case from the product description that's being uploaded. And all these features are then passed to tens of thousands of decision trees we have to make that decision. And finally, the classifiers tell us, is it clothing, is it electronic, is it book, is it something else? So let's say if it's clothing, then it goes down and says, is it a shoe, is it a shirt, and so on, and it's further down. So a typical taxonomy, if I remember correctly, at Ichiba is about 5 levels down. So you can imagine this is level 1, level 2, and then there are 3 levels down. And the total tree roughly is 40,000 nodes. So it's an immense classification system. Now the interesting question to ask is, does it work? Well, we have done the statistical test, so I can tell you it works, but let me try to convince you. And this also demonstrates my knowledge of some of these products, which is mostly absent. So here's an example of a new title. Here I'm just only showing you the classification results on title. I'm omitting the description that we also use. So somebody uploads a new product. It's called cross-front peplum layer dress. I have no idea what it is, except I can understand this word, dress. So I assume, okay, it's a women's dress. But beyond that, my knowledge is 0. Okay, but computer, fortunately for us, is much better. It says, well, it's women's clothing, but it also knows a thing or two about these words that it has seen in the past. It might have seen peplum somewhere, it might have seen cross-front somewhere that is existing in the database. So it says it's party and cocktail dress, which actually is correct. Now it gets even more interesting. Somebody else uploads cut out leather platform wedge espadrilles. I have no idea what this is. Like, I can't even say what the top level category is. But it turns out it's a shoe, but not only a shoe, it's a specific type of shoe, it's pumps. I have no knowledge of pumps, but I'm glad at least my classifier knows what pumps is. So that solves the problem for us. So this is what we're doing for classification. Let me switch to the second key task, which is searching. Now, searching a product catalog of 300 million items is an immense task. And we are doing a very, very small part. We have a fantastic team in BDD which supports us. We learn a lot from them. And we get a lot of help from them. So that's why I don't need to say that we are the only ones doing it. But it's very interesting technology that we are trying to build with searching. So here's a real example. So somewhere in the US, this guy comes online and he wants to find a compact desktop computer. That's what he's thinking. So he goes online and he types a search query called Lenovo ThinkCentre. And he gets some search results on the side. He looks around, he browses a little bit, doesn't like what he's seeing. So he goes and changes the query. So instead of Lenovo ThinkCentre, it says Lenovo All-in-One, and he gets some results. He doesn't like what he's seeing on page 1. He goes to page 2, browses everything, doesn't like anything. Goes to page 3, doesn't like anything at the top, but finally finds a Lenovo ThinkCentre hiding in the bottom, which is something that he wanted. It's a compact desktop computer. And this is a real example which we extracted from our data. And this person proceeded to buy this $1,000 computer right after that. Very quick transition once he found the product. So search was key, and he did not hesitate to spend $1,000 on the platform. But the interesting thing is, once he's searching with Lenovo All-in-One, because it's a text-based search, everything else that mentions Lenovo All-in-One will be visible in search results. So you have things like CD-ROM drives, you have things like network card, because they're all matching on the text. So what's happening is text matching is working precisely as we wanted, but the products that are really, really relevant sometimes are hard to find. And that is what we want to fix. So the current situation is the relevant product is hidden somewhere in the lower end because of issues with text matching. We want to switch to an ideal situation where the first query he writes, which is Lenovo ThinkCenter, surfaces the product he's buying as the second product or as the first product at the top of the first page. That's our goal. Now we know that text-based search alone isn't working, so what else can we use? And how can we do this job of learning a model to solve this problem? So it turns out there's a very, very nice paradigm called learning to rank. It's a very fancy term for something very simple, which is basically you're the teacher and your machine learning model or computer is the student. What the teacher is telling the computer is, hey, for a given query queue, I will tell you the relevance of all the documents, or some small set of the documents. You tell the computer for Lenovo ThinkCenter, here's the relevance of the different documents. You're teaching the computer on the fly. And you can do it on the fly or you can do it in batch mode. We do it in batch mode. We give a lot of training data. And it's easy to actually get this data. I'll tell you a trick on how we actually do this. Because in reality, you need millions of examples for this. You can't hand annotate, so there must be some way to do this at scale. So once you have given, the educator, the teacher has given to the computer some relevance criteria or ranking, we learn the system, end up with a model, and for a new query and candidate documents, we're able to rank them appropriately. So the key here is how to decide the relevance. We know the text-based one is not working. There must be something else we need to use. We want to use something called user behavior signals. What are these? Well, user behavior signals are basically what you see users doing on your platform. For a query, once they get the search results, you measure what are people clicking on, what are they browsing, what are they adding to the shopping cart, and finally, what are they buying? And this gives you that relevance ranking. Buying has the highest relevance because this is where the customer is spending money. Adding to the cart has next highest relevance because the customer almost made the decision to buy. Clicking is very useful compared to no clicking. So as you can see, highest relevance, second highest relevance, third highest relevance, and no click is fourth or others. So this is what we do to get scalable data of millions of relevance rankings for millions of queries to train the system at massive scale. It's pretty cool when it works. Here's a result of an actual query. So somebody actually goes to the platform and is looking for a 40-inch TV. Again, this is a very expensive item, could be $500, $1,000, so high-ticket items, and you want to show them relevant results so they can buy. If you only do regular text search, you will get things like TV mount. This is used for mounting the TV on the wall. Why is this here? Well, the query is 40-inch TV, and 40-inch TV is in the title. You get other non-relevant things like a film to protect the front of the TV. Well, why is this coming up? It says 40-inch TV in the title. So if you do text-based search, it doesn't work all the time. But if you look at over many, many queries, what are people actually buying and clicking and adding, you see that people will now almost never click on these things. They'll skip, they'll go down. So this is what we are measuring, capturing, and learning. And in the new system, these things are pushed way down. So customers don't even see them. And they get relevant results that other customers have in the past clicked, added, bought for similar queries. So that was what we are doing for searching. So let me summarize quickly. E-commerce data is primarily unstructured, overwhelmingly unstructured. Almost everything is unstructured. The product catalog, which is the biggest piece, is unstructured. Has images, has product descriptions, has titles, they're all unstructured. There are other things that I have not even covered, which we are working on. Some of my team members are working on merchant and item reviews. So understanding the text that customers are writing for merchant review, for item review, which is all unstructured text, of course, and search queries, and even understanding the query that people are typing is unstructured. So given that it's primarily unstructured, properly organizing all this data and precisely searching it is key to make sure that our customers find the right item quickly, efficiently, and they leave happy. That's all we're trying to accomplish. So thanks a lot for your time today.
Try and use this one. So we're ready for the Q&A. If anyone's got any questions, please raise your hand.
Thank you for the session. For unstructured data, I specifically want to ask questions around images, like you talked about text. But for images, how does this work?
Thanks for the nice question. So for images, we have several projects in our different departments. Image understanding is actually even harder because the amount of data we're working with is at a larger degree. Also, images can have modifications done to them by people who are uploading data. They may put their own icons or some graphics, so it obscures the actual product that's being shown. So we do have some deep learning techniques in RIT Tokyo. We work with folks who are working here, and they have a fantastic system where they're able to classify what we're doing. And Paris team actually also works on. So Hirai-san showed the example where in Rakuten and Price Minister, if you take a picture, it classifies. Now, eventually what will happen is this technology will be put together with that technology. So when the merchant uploads images and text, all of these things will be transparent to the merchant, and it'll give one answer based on both image understanding and text understanding. I hope that answers your question.
How this machine learning is helping merchants to optimize their text, or how they increase their sales?
Perfect. Great question. I should have covered that in slide. Here's a simple example. You upload a bike, it gets put into an umbrella category. People will never find it when they're searching for it. Because one thing that happens is in search systems, in browsing, where the product exists today is used as a signal in search. And browsing, people go by category. So there are these two primary ways. And for instance, third primary way is search engines, external search engines like Google and Yahoo. But they also take metadata into account. So if your metadata is wrong, which is what it means that classification is wrong, all these three systems will break down. So merchants benefits by, if the customer is not able to find the item, they don't get any sales, don't have no GMS.
I mean, do you give any data back to them, like at their disposal, saying, hey, because what happens is merchants become desperate, they add too many images, too many text than required to attract sales. And sometimes because of there is too many data, customers who are trying to buy, they get confused and they avoid the buying decision. So how this system help them saying that it is time to write small text, relevant text.
Yeah, so I think what you're referring to is data modification.
Mhm.
So we are not doing data modification in this scheme of work. We're basically doing data classification, data understanding. Data modification is a much harder task. It depends on what level you want to do it. If the level you want to do it is simply provide feedback to the merchant that this approach of using 50 images or writing pages upon pages is not working, that is much easier because that you can figure out from what the patterns of successful merchants are versus the unsuccessful merchants. But if you actually want the machine to do the data modification, that is, I think, we are probably still about 5 to 10 years away from. And we probably don't want to go and modify without merchant's permission anyway.
Yeah, I mean, what merchant is getting from Rakuten in a dashboard way, so obviously it will be maintained or controlled by human, that is merchant, it's merchant product. I was just wondering, like you have 40,000 and several million product,
Right.
and people are coming, and how hopefully the conversion rate is not like more than 5%, so 95% are not buying. Why they are not buying? Because there's a conflict in information.
Yeah, so Ichiba has a very, very nice team that's called Merchant Advocate Team. They have some of these best practices that they have learned over the years and know which work. And they are the ones usually who reach out to the merchants. So we are sort of building technology that makes it easy for that team to get insights. And because they are operating at much higher intelligence than us, they are human intelligence, we're still much lower. We're just making it trying to make it easy for them. We're not trying to do the final job. I hope that answers your
Thank you
question.
very much.
Sorry, we have to wrap up here because I think the next sessions are going to start soon. If you could give another round of applause. Thank you.
Thank you. Thanks for doing the back and forth.
No worries, yeah. We'll see what.
Thank you. Thanks for so image actually, let me introduce you to Laurent actually.